a little bit closer in your interval because you know you're going to be hitting what you expect to hit. When you don't know what your population standard deviation, you're not really sure. And when you notice this is when the margin of error happens too, is like now with all this polling business, and I always keep going back to the polling. The first time through, how do I estimate who's in favor of Rubio or Cruz or Trump for that matter? You know, who's in favor of them? I have no background knowledge on, they never ran for president before. I have no background knowledge on what people think of them. So we have to build that up a little bit first. So therefore, their true results might not be as close once we realize what the population is voting for. So do you kind of see where we need to really know your population standard deviation? So when we don't know it, we use a T distribution as opposed to your Z distribution. And the nice part about this is your calculator also said Z interval for this guy. It will say T interval for this one. If you use your calculator, that's the biggest part right here. How to tell is if we have your standard deviation from your population. So we're looking at properties for your T distribution. Your mean and median, your mode are 0. You're on a normal. This means we're on a normal curve. It's bell-shaped. It's a normal curve. Area under the curve is still 1. But what happens is there's little tails as your sample size changes. So you get more of a curved look here. And it keeps like getting closer and closer to the mean. But there's all different curves. The area under the curve is still 1. But they call it these little tails. If you take a look at the bottom of 311, you could kind of see the little changes in the graph. And it's affected as it gets closer, as n gets closer to 30. This is a little bit closer in here. You're going to see it switch a little bit over. And they'll get closer and closer. It changes again as your sample size changes. And they call it a family of curves. The most important part you have to know is the degrees of freedom. Because we work off of a degrees of freedom. We take your sample, which is n, and to find your degrees of freedom, we do n minus 1. So in the other one where we divided this, we're going to change this now. We're going to use your degrees of freedom and find a little something different because we're not going to be able to do that because we don't know your population standard deviation. Degrees of freedom are like this. Say you play musical chairs. I pulled 10 people up here. I have 9 chairs, right? So everybody gets a chance to come in and sit down. Come and sit down, and then I get rid of the chair. That last one only has 1 chair, 1 assignment. Same thing if I lined you out in the hall, and I had 25 kids in here. I have 25 chairs in here. So one at a time you walk in, I say, where would you like to sit? You choose a chair, right? It's your freedom of choice. Does that last person get a choice? He's stuck wherever that last seat is. So therefore, that's a nice way to think of it is n minus 1. That last one doesn't have a degree of freedom there. That last choice is not going to be there. So we always take the sample and we subtract it from 1. We're going to use a different table than your table 4, and you're going to see the degrees of freedom, which is what's nice about this because your table kind of helps you remember you have to use degrees of freedom. After 30, you get closer and closer to a normal distribution. And I forgot to copy table 5, but we're going to be looking at table 5 to find your critical values. We do this just a little bit different. You know our ZC? We put the 90 in the middle. We subtracted it from 10, divided it in half. Our T is a little bit different. We do have an inverse T. It works like the inverse normal does, but most of the time you're going to go right to this table. If you take a look at, they gave you a little sample table on 311, and if you notice at the top, 311 as their table. This is table 5. It has a couple of headings. It says level of confidence C. It says 1 tail, 2 tails. It's got a little alpha sign next to the tails. We don't use those for this. All we use is the top one, where it says level of confidence C. And look at the left-hand side, CDF, that's degrees of freedom. So when you go to look this up, you'll notice it doesn't say N, it says DF. So it kind of forces you to take your N minus 1. I like the table for that reason. So if I'm looking up a ZC for an 80% confidence interval, I'm going to look under the 80% confidence. I'm going to find out what my sample size is, subtract it from 1, and I'm going to pull up what my TC is going to be. So it's a little bit different than using your Z-score. Notice there's no negatives, there's no positives. They're all positive values. There's no negative T-score, negative Z-score. You know, we're working a little bit different. But I do like table 5 because it forces you to remember your degrees of freedom. Then your N minus 1. And we'll take a look at how we get there. So if you take a look at this example, and we'll read this and then we'll go to the chart in the back. They want you to find a critical value, TC, instead of ZC, we want to call TC, for a 95% confidence interval, confidence level, when your sample size is 15. Now, follow that chart. Level of confidence, find 95. See how they highlighted the 95 column? Now you're doing degrees of freedom. You're not looking up 15. You're looking up N minus 1. 15 minus 1. Your degrees of freedom is 14. So you're looking at this, 14.95. That's how easy this is. You no longer have to make that little thing that we did before. If we had 80%, if we had 95% before, we put 95 in here. We did 1 minus 95. This is what a lot of you forget to do. Divided by 2 and find your Z-score for that. Remember that? We don't have to do that for this. Life is easy. You look at your table, find your degrees of freedom. This is labeled level of confidence. We find a 95% confidence level. We find your degrees of freedom. There's your TC. It's a lot easier than finding your ZC. So we find your TC. They're always positive, just as your ZC was always positive. Even though we looked up the negative value, your TC, your ZC was always positive. So let's find another one here. Find me the critical value for a 90% confidence level when your sample size is 22. Now you're going to have to go to the back of the book for this. They didn't give you enough room on that table. So go to, I'll tell you what page. Page 818. It's table 5, page 818. You only have one side. Like the Z-score had 2, a negative and a positive. This one is very easy. Notice, if you take a look at, like they come down to 40, then they jump to 45, then 50, then after 50 they go by 10s, until they hit 100, and then they go to 500, they go to 1,000, we're never going to hit that high. So, you're not really going to use a lot of these, because if we do, we probably would do the Z-score. So, we don't really use too many of the high ones. And according to our book, we would never ask you to extrapolate anything. It'll be in your table. If you need to find it, it'll be in your table. Yes. Yes. So everybody try to find the TC associated with that confidence level. Use your table A18 in the back. I'll make a copy of this for you guys to hand out. So look across the top, level of confidence, find your 90, and what am I looking for along the side? N minus 1. 22 minus 1 is what? 21. Find me that. That's it. That's your T6. That's how simple it is. Your Z-score, you had to subtract it from 1, divide it by 2, do an inverse norm. This, you go right to your table, you find your TC. Now, when do we use this guy? We're going to put it into your formula. Here's your formula. Your other one used to say ZC. I no longer have a ZC. I no longer have a population standard deviation. I do have a sample size. This is your sample size. This is not your DF. But there's your TC that you just found. That's how easy this is. We have to give you a standard deviation from your sample, or if they give you a set of data, this is where you're going to find it in your L1 under your SX, if we make you find it. But the rest is pretty much going to work the same. And we build your confidence interval.
So what is
S is your sample standard deviation, because you don't know your population. Our other one was this. And E was this. Because we knew our population standard deviation. We had to find this. This can't happen anymore, because we don't know what your population standard deviation is. So because we don't have this, we can't do this either. We have to have a special little thing in here. So let's take a look at something. I have a confidence interval of 90. And I have N is, let's make it very close. Let's make it 20. Let's see where the difference is. So when we did your Z-score, we said, here's 90, 1 minus 0.9, divided by 2, and we looked up our Z-score. I think this was 1.28. Okay, we looked up our Z-score. Find me a TC for 90. Find me a TC. Maybe if I show it to you, you'll see a little bit differently. Oh, this is 1.645. Find me your TC.
1.729.
Ah, 1.729. Look at the difference. The ZC is 1.645. The TC is 1.729. What difference should that make? What should it do to my margin of error? Increase it. Why?
But they're not equal, so that increases.
It increases because I'm multiplying by a larger number, right? Here was your old one. I realize we're trading this off, but N is staying the same. And this guy is actually increasing. So if I multiply by a larger number, shouldn't I get a larger number? Right? So it's going to change my margin of error.
What was the margin of error? Oh, that's the margin.
This is your margin of error formula. So it's very similar to the other one, but the problem is we don't know your standard deviation for your population. So therefore, this is the guy that drives it right here. Because we don't know this, and we have to use your sample, I'm not so sure that you got me the best sample you can for this population. So therefore, I'm going to give you a little bit more wiggle room in here. I'm going to use this answer, TC. Multiply it by a little bit larger number. So I gave you a little bit more wiggle room because you know what? Maybe that sample wasn't the greatest representation of your population. And I don't know what the population standard deviation is. Once we know the population standard deviation, we're okay with that. But when we don't, there's a little bit more uncertainty. So to take up that slack, not a lot, we just multiply it by a larger number, which gives us a little bit more wiggle room. The key is right here, because you don't know this guy. So play with the number, give me a little bit bigger. The rest of it all stays the same. The rest of it's going to be the same regardless of what we do. Make sense? I like if you could understand this part, that the TC is slightly larger than your ZC. So let's try this. And after we do this with the formulas, I'll do this with your calculator as well. You randomly select 16, and you're going to find that n usually is smaller when we do this. Because we don't know enough about your population, you're probably not going to be able to research and get too many in your sample size as well, because it's not a usual thing. You randomly select 16 restaurants and you measure the temperature of the coffee sold at each. The sample mean temperature, this is your X bar, is 162.0 degrees Fahrenheit with a sample standard deviation of 10.0 degrees Fahrenheit. Find the 95% confidence interval for the mean temperature. Confidence interval means I need to have this. I need to make an interval to and from. Assume that your temperatures are normally distributed. If n is less than or equal to, if n is less than 30, we have to tell you that it's normally distributed, or you can't even do this. Now, normally we had your z-score and your population, but because we don't know your population, we're going to use this. We have to find the TC first. This is much easier with your table. So your table says your level of confidence is 0.95, but it's looking for your degrees of freedom. What are your degrees of freedom? If n is 16, what's your degrees of freedom? 15. N minus 1. So find me the TC from your table. Look at your table. Very easy. Level of confidence is the title of it. That's the level of confidence, and degrees of freedom says, well, where do I get degrees of freedom? Subtract 1 from my sample size. It's that simple. So find me your TC. What'd you get? Good. Perfect, because you don't even have to worry about how many decimals. It's all right there. Plug it into your formula. And it's already positive. We got the S. We got the N. Make sure you use N over here, not the degrees of freedom. Plug it into your calculator and find me your margin of error. And since the mean is rounded to 1 decimal place, round your E to 1 decimal place. So tell me what you get for your margin of error. .3. Good. Now all we got to do is build it. Your mean is 162.0 plus or minus 5.3. And you could write it either way. You could give it to me this way, I'm fine. Or if it makes more sense, write it out the long way. Because this is what's going to help you interpret this. You want to be 95% confident that your population mean temperature for your coffee for all the restaurants in the population will fall between 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit. Not your sample mean, because you know what your sample mean is. You're estimating your population mean.
Okay.
Will says okay, good. Really, this is the easy one, isn't it? And isn't it making you remember back to the other one? Okay, so watch how easy this is. Maybe.
It's coming
Me.
back. It's all back.
It's coming back to you. So watch. Stat. Test. Before we did a Z interval. We're still in an interval. But none of these have the word interval except here. But I don't use a Z-score anymore. I use a T-score. So travel one down where it says T interval. Bingo. So, put your sample mean in, 162. Put your sample standard deviation in, 10. Put your N, 16. Look, you don't even need to find your TC here. Put your level of confidence, calculate. Is it 95? Yeah. Now, there's my interval. I rounded to the tenths. So if you just round to the tenths, now you can still work yourself backwards. You can take this high one, you can subtract your mean. There's your margin of error. You can still use your calculator and work yourself backwards. Just like we did with your ZC. All right, you guys do try it too. Now, you use your calculator. Life is a piece of cake here. You only have to change one thing each time. I'm going to pull up the other one. For 95, we had.
How do you do your calculator?
Go to stats, test, and come down to 8. If you're working off of your margin of error, you're just going to have to repeat this. You're going to have to change this for your confidence. And I think our N was 16. So your degrees of freedom is 15. So here's a 90. Here's a 99. But this was our 95. I'm going to put this on the number line. So we're going to see if the same thing holds true. What held true on for your ZC? The higher the confidence level, what happened to the interval? I want to be more confident, so give me more wiggle room, wider. A lot of you got that wrong on your quiz. If you want to be more confident, you got to get a little bit more wiggle room. Give me a little wider interval. I don't need to be as confident. I don't need as much wiggle room.
What if I put increase?
I still gave you credit.
Alright.
I put the word wider, but I gave you credit. You know I'm hung up on that. It's got to say wider.
I wrote increase.
Broader. Okay, so if you're doing your formula for this, what was your TC? Anybody do the TC for this? Good. The rest is going to stay the same. Your sample standard deviation, I didn't write it down. 10? Thank you. Over N. And what was your TC for 99? Good. So do you see where it increased from here to here? We're multiplying by a bigger number. It's got to increase your 8. If you add something bigger, it's going to make this wider. And the rest stays the same. God bless you. So your margin of error is going to get larger. So I'm going to start with 162 plus or minus 4.4. So let's do this guy in red. So let's see where this lands. 157 falls here. 164, 166.4 falls here. This was a 90%. Okay, I don't need to be as confident. Okay, 99, I need to be more confident. Let's put this in green. 154.6, 169.4. 154 falls here and here. Isn't that my most confident one? My most confident one means the widest one, right? Yes.
If you do like a problem and you see that we need to help,
You can use calc.
you just help on the top so you know what.
I just need your steps because here's the problem. If you use the calc and you use a z instead of a t, your answer is wrong. And then I can't give you any credit. If you say z interval and you just write me down what you put in there, I knew you knew how to do it, but I knew you just went to the wrong one. You just use it, you lose a little credit. So that's the only problem with the calculator. And that's one of the major things. The z interval comes first. When you look at your calculator and you look at your test, here's the problem. The z interval comes first. You don't see the t. And yes, this is a t, but I can't tell you how many kids just automatically go to the z because that's what's showing there. So if you do a z, your answer is completely wrong. I have nothing to go by. Also, even if you do this and you enter the wrong standard deviation, I don't see it. So your answer is still completely wrong. That's the problem with the calculator.
So we don't need to write down the TC or the Z.
Not if you're going to use your calculator.
Is there
If
any
I
way to
ask you
find
for
it?
your well, not the TC off of your table. Or you can
Or
do an
table.
inverse T. I can show you inverse T. But if you do your margin of error, you know how we just subtract your mean from your upper level? Just subtract your mean from your upper level. There's your margin of error. Like if I did this on my calculator, but I needed to see my margin of error, I just subtract my mean. Oh, there's my margin of error. Just like we did in the other one. There's my margin of error.
So what's inverse T?
Inverse T is how you can find your TC. Inverse T is here. Yeah, but you have to do it the same way. You have to say 1 minus, let's do 0.95. Which one do we have here? 99, I'll do 0.99. It's the same as the other one. I like the table better for this guy. I think it's less work on the table. And our degrees of freedom was what? What was our sample? Okay. So this should give us our, it's the same as your inverse norm. And you just have to turn it into a positive.
So for confidence, it's always 1 minus confidence divided by 2.
It's the same as your inverse norm. You take the 1 minus confidence because it has to fall in the middle. It's 99% of it has to fall in the middle. So if that's where you're going to make your mistake, that's a big mistake. I just think the table for table 5 is just so easy to read. You can't go wrong with the table because it says level of confidence across the top. It says degrees of freedom. You can't even put your n in there because that's, you have to do n minus 1. You still have to know degrees of freedom to do the calculator. I mean, I still get kids that you can absolutely use that instead of using the table. Absolutely. But I think it's easier to use the table on this one. The Z table, not as easy. Because the Z table, don't forget, has a positive and negative side. And then everybody complains, about doing the 1 minus thing and whatnot. All right, let's try one more. Can you kind of see where our difference is? We don't have a real big difference in here. The fact that we don't know your population standard deviation is our major hit. All right, let's see if we can squeeze one more in here.
So find the Z-score inverse is the one that's the same thing as ZC.
That's your ZC.
Yeah, Z-score.
Yes, and inverse T is your TC.
So you can call that T-score inverse.
Yes. Let me jump down here for a second. Let me jump down here. Here's what you're asking. Here's where you need to know which one do I actually need to use. So what runs this is your population standard deviation. It says if you know your population standard deviation, chances are you're going to end up using a Z. If everything is normally distributed, you have a normal curve. If I don't know this, I got to use a t-score. I got to have a little bit extra. And if you really look at this, here's your major difference. That one, and I didn't know my population standard deviation. I didn't know my population standard deviation. And you know your n minus 1? I don't know if you remember back when we first did standard deviations, and we did that big table, and we divided the standard deviation thing underneath the square root by n, and for the sample, we divided by n minus 1. It just made it a little bit bigger. Your sample standard deviation just a little bit bigger. Doesn't it just deviate off the mean just a little bit more? It just need to be a little bit closer. The one thing that you have to be careful about are your samples. This really runs your whole experiment. It runs everything that you base your inference on is your sample. So as careful as you are, you do everything right. You sampled systematically. You took every third person that walked in the mall. You did everything systematically. Maybe that day you didn't get a very good sampling of people. Maybe that day something else was going on and people stayed home or went somewhere else or did something else and you didn't get a really good sampling of that. Maybe it was a really bad weather and older people don't like to come out in bad weather, or people with a disability don't come out on bad weather. You know, so your sample didn't really give you a great representation of your population. You certainly don't want to do your whole survey all over again. You know, you probably would use this and say, I need a little bit wiggle room. And a lot of times with this also, you don't know what your population standard deviation was. This is the first time I ever did this. Next year, yeah, I'll know what my population standard deviation was. I have some background on this. This year, it's new for me. So I'm going to have to use a sample and rely very heavily on my sample. So that's where this takes us. That's the biggest question. So really, all you're doing is this. Basically, this part stays the same. You're still making an inference about your population, regardless. Tomorrow we'll pick up more on this. We'll do example 3.